Lesson 73, collisions. We will refresh our understanding of collisions. Now this lesson's a refresher lesson because we've already done collisions. And as I said to you guys, when we did collisions all the way back in lesson 68, I said, you don't need to know this for a test. It's not expected. And then next thing I know, it's like, oh wait, actually you do. So I already gave you guys a little bit of practice on this. What I'm going to do now, though, is I'm going to give you a fair bit more practice on this. But I guess because you guys have done this already, you guys probably won't need too much practice. You guys did also surprisingly well on the challenge question, which was related to collisions at the end of the quiz. I didn't expect as many people to get that as a correct answer. But yeah, a lot of you guys actually figured it out. So I was actually quite proud of you guys. You did really well. That quiz was really informative. It told me a really good job of where you guys struggle with. It actually showed me, believe it or not, that you guys are getting about 70–80%. It actually showed me you guys are doing pretty well. I don't need to stress too much about you guys forgetting some of the stuff. You guys have got a lot of it in your brain already. This, by the way, this topic today is going to be a bit of an extension anyway, so it's not really going to be anything new. So let's go back for a bit and see where we've come from to get to this point. So before we got to this point, we started off, let's go all the way back to here. When we first learned about momentum, lesson 67. Momentum is an object moving. An object has a motion. Momentum is calculated by mass times your velocity. We then did some calculations of basic ones, and then we looked at what happens when you have a collision where the two objects stick together. This is actually what the basis of the question was at the end of the last the quiz, except the difference was instead of telling you guys to work out what the speed was, I told you what the speed was, and I asked you to find out what this mass was. And that was actually easy to do because you could find the net mass here, and then because you knew this was 2, you could work out what this one was. That's how a lot of people did that. We did some more ones. We did like what happens when momentum gets passed from one object to another. And we did what happens when objects get passed, but the other object bounces backwards instead. And that's fine too. We did those. And then what we did was we started to talk about impulse. Impulse is, of course, a change in momentum. If you just look at that 2 kilogram mass, that 2 kilogram mass has swapped from 4 meters per second to the right to 2 meters per second to the left. So that's a change in 6 meters per second. And there is, and we can calculate a change in momentum, and eventually that gives us a force. A change in momentum is an impulse, which is force over time. We used impulse to give us an idea of what it is. Impulse is a change in momentum. Great, cool. We looked at some more examples. Then we talked briefly about torque. We said torque is a force times a radius. We gave some examples. We looked at negative is anti-clockwise, whereas clockwise is positive. We did some calculations. And then we did some complicated ones where we looked at what happens when we have a system of torques, more than one torque, built up together. And we put all these together and we solved 2 big problems, and we solved this one too, which was actually pretty challenging, but we got through it. And then I set you guys some work to do. I forgot to get rid of the working out. That's fine. We worked out all these bits and pieces. And I set you guys some work to do. We did structural design, and that was about it. So what we're going to do today is we're going to talk about collisions. But before we do collisions, I wanted to quickly finish off one very, very last thing about torque. And that is the classic sine problem. Not sine as an inverse sine cos tan, but just as in a sine sine problem. And I love this. This is a type of problem, and they don't actually put this problem in the other textbooks. So I thought, you know what? I'm going to show you this type of problem just so that you don't get caught out randomly. But you guys should be pretty comfortable with doing this anyway. But let's have a look here. An advertisement banner is hung by 2 cables to the ceiling of a shop. The banner has a mass of 45 kilograms. The cables are an angle of 30 degrees to the vertical, as shown in this image. Below, if the mass of the cables is ignored, calculate the tension in each of the cables when the sign is suspended. Use G equals 9.8 Newton kilograms, 9.8 newtons per kilogram when answering this question. So that's just sort of the acceleration of gravity. It's a weird way. That's a weird way to write acceleration, but okay, whatever. So how do you do a question like this? And by the way, ladies and gents, if you are going to copy this down, don't try and write down all this text. There's way too much text here. How do you do a question like this? So we want to know what this tension force is for each of these wires. Now, the best way to calculate this tension force is we know that the net force, this is how I would approach this question. We know the net force acting on the sign equals 0 because that sign's not falling down. Okay? Now, if we know the net force acting on this sign is equal to 0, then that means I could approach this by saying, well, what are the forces acting on the sign? We have a force upwards, and we have a force down. Our force down is caused by gravity, which is going to be the mass, which is 45 times 9.8. Minus, because it's downwards, we're going to go 9.8 times 45, which equals 9.8 times 45 equals 441. So therefore, we've got 441. Let's not get ahead of ourselves. 0 equals a force upwards minus 441. So therefore, the force upwards needs to be 441 newtons. Now, I'm being actually very careful here. I'm not saying that the tension force is 441 newtons. I'm saying that the force upwards needs to be 441 newtons. So, okay, how can we then approach this? How can we then figure out, well, how much force is getting pulled on these by these how much of this force is going to be pulled by these different objects? And we can rely on, you could sort of think that as like, well, we could divide these by 2. There are 2 sort of ways that I think I would like to do this. We can use torque, or we can use just basic logic sense. I think maybe because we're doing a subject about torque, maybe we should use torque as our go-to, but because these are, and the reason we're going to use torque is because these angles are the same, but that might not always be true. So let's grab a look at this, how to do this question if we were going to do torque. We're going to do the same principle that we used with the bridge. We're going to assume that one of these positions is fixed. We're going to fix this position here. And we're going to say the net torque equals 0. So that means that net torque equals 0. We've got to torque downwards, and we're going to torque upwards. Okay? Now that torque downwards is going to be 0 equals, that net torque downwards is going to be, crap, okay. No, I was right the first time. Can't do it. You could do it this way if we knew the length of the sign, but we don't know the length of the sign, so we can't do it this way. So what we're going to do is we're going to do it the other way, which is using symmetry, which is using our brains. If we know that the net torque, if we know the net force upwards is 441 newtons, then this component here, this upwards force, must be half of that. So half of 441 equals 220.5. So this force upwards is 220.5. But here's the kicker. It can't apply that force. It can't apply 220 newtons, 0.5 newtons upwards because the cable isn't straight up and down. The cable is at an annoying angle. And that means not only is it pulling upwards, but it's also pulling to the right. That pull to the right is cancelled out by the pull to the left by the other one, but we need to calculate this. So we've got this annoying angle here. 220.5, we've got 30 degrees. We want to know what this force is. If I label this triangle, we've got hypotenuse, opposite, adjacent. We've got, in this case, 220.5. We've got adjacent, hypotenuse, cosine theta equals adjacent over hypotenuse. Cosine, and we want to know the hypotenuse. So therefore, the hypotenuse is going to be A divided by cosine theta. What's A, you say? A is 20.5 divided by cosine 30, which equals, this should be more, by the way. If you get an answer that's less, then you made a mistake. 20.5 divided by cosine 30 is going to give you the answer of 254 newtons. That is our tension force. 0.6, sorry, whoopsies. 255 newtons. Please tell me, calculate the tension. So that it's 225 newtons at 30 degrees from vertical. That'll do. And that can be used to describe our tension. Now that tension, as I said, is more than the force needed to pick up the sine, and that's because that force, it's going to be 220 newtons upwards, and then there's going to be a force to the right. We can call this force X, and we can call this force to the left negative X. And those forces, by the way, they're going to cancel out. That's going to give you, that's why the sine's not rocking to the left or to the right. Now, and the reason we can do this in this way, the reason and the main big issue that is this step here, and this is what I want you guys to be very careful about. The reason we can do this here is because we have symmetry. Because we know the sine is the same on the left and the same on the right, has to pick up the same amount of mass on the left and the same amount of mass on the right. If these were different, we could have ourselves a bit of an issue if these weren't the same. I think if these weren't the same, they would still have to pick up the same amount of force, and you could still divide that by 2 as long as it's a as long as this sine is a uniform density, you could just divide it by 2. But it's, in this case, we can assume that they're both the same tension because they're the same wires. Are there any questions about this? Are there any queries or any points that I went over too quickly that you want me to go back over? Let me open chat. Do you guys, give me a yes or a no in chat. Do you guys think you could do a question like this on your own? Who thinks they could do something like this on their own? Probably not. What about anyone else? Is anyone more confident than Rochung? Does anyone reckon they could do this on their own? All I'm doing is calculating the upwards force and then just figuring out what angle that tension force needs to be at. Anyone more confident than Rochung, or anyone less confident? Anyone's like, yeah, definitely not. Maybe yes. Anyone else? I love these, not fully yes, sir. Cool. All right. So you guys reckon you can do it? Cool. Well, 2 people reckon they can do it. Good. Go. Give it a try. I'm going to give you guys pretty much the same type of question. It's a smaller sine. I'm going to give you guys 5 minutes to try this. I'm going to actually set a timer, and then I'm going to work out the answer, and then I'm just going to write the answer down. I'm not going to solve it. I'm just going to write down the answer. So you got 5 minutes to try and solve this. Go. Bang. All right, I got an answer already. Then again, I'm the physics teacher, so it makes sense that I can get an answer in a minute. But, you know, that's quickly. Yeah, thank you. Firstly, quickly, thank you for putting that privately so that you don't give away the answer to everyone. That's close to what I got, but that's not the same thing. Let me just check. I have a theory about what you may have done. Two people. Yeah, let me just double check my end. Maybe I got the wrong answer, ladies and gents. I've got, yep, 2 answers so far in private chat. It's really good. Yeah, that's what I got. Fouckley Kelvin, you guys are correct. You in your private chat. Tam, not quite. I mean, unless you're trying to. Like, ooh, Yvonne, good answer. The other gentleman just gave me a number, but you give me a value and a direction because it's a vector. Really good answer there. Tam, my guess is that you've done it. You've got a direction here, but remember, we're looking for the tension in the wire. So you're looking for the hypotenuse of the triangle, not the opposite side, is what I think you may have done. Yeah, that's okay. That's all right. Take your time. I bet you used tan instead. That's all right. Answer's going to go up. Yep, perfect. Perfect. Good job, Tam. I'm going to put the answer up in about 1 minute if you haven't got it already. Haven't seen an answer from Phoenix yet. Haven't seen an answer from. Have I seen an answer from Vu? Were you the first one? I haven't seen a. Oh no, I haven't. Yeah, I haven't seen a private answer from Vu yet. Oh, good job, Leon. Give yourself a pat on the back. You haven't given it you haven't put down units and you haven't put down a direction, but you got the right value. So I'm happy with that. All right, I've got the clock coming down to about the last 20 seconds. Is there anyone that can get me a private answer in before the time runs out? I'm looking at Vu, looking at Phoenix, Andy. Ooh, Eddie, that's a bit too much. I don't know how you got that answer, but it's a bit too high. You're close. Yeah. All right. Ladies and gents, I'm going to write down the answer now. The answer, which is I'm just going to write down pretty much exactly what Yvonne wrote. The best way to answer this is the tension force is 32 newtons at 40 degrees from the vertical. And that's pretty much the best way to answer it. A couple of people just saying 32, or a couple of people saying 31.98. That's fine. 32. Yep, thank you, Arn. Good job. So that was just getting you guys a little bit of practice in how to deal with these types of questions. Now, you might not get these types of questions, but again, it's more practice for you guys dealing with angles. Because remember, in physics leading up to year 11, pretty much we just said, yeah, everything works at right angles. But now you guys need to start learning that that's a perfect world. In year 11, we're going to deal with like mirrored symmetrical things. But, you know, as I said, in year 12, I could give you a question like, you know, like this and say, well, you know, what's the force on each of these wires and blah, 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 and, you know, so on and so forth. This would be kind of difficult because this is going to pull it to the right. So therefore, yeah, we're not going to deal with that because that would be very, very challenging to do. That's actually not going to, I don't think that's physically possible because it's going to swing. Whatever. Point is that, yeah. Now I've got 2 extra little slides to do. We've got 1 more question and then that's going to be it. Now, as I said to you guys already, collisions are something that I'm only putting this like pretty much there's nothing new to copy down here. I'm just restating the facts here. Collisions are something that we've talked about already. The main tip with collision calculations is to remember that momentum must be conserved. That means that, what does that mean? Momentum being conserved? That means all the momentum of all the objects at the start must equal the momentum at the end. So if you take every single object, and if you've got like, it's very rare, but if you had like 3 objects, you know, if you had like 2 objects hooked up to a spring and they had 0 momentum at the start and then later on they're flying out to the right and to the left, even if you had 3 of these, you know, 1 to the bottom, the momentum of all of these things must add to equal 0. Now we're not going to deal with more than 1 dimension, but yeah, like these have to add to be 0. Plus, momentum is a vector, so you can have negative momentum. In fact, in this case, the momentum p equals 0. In this case, you might have the momentum, and this might be plus 2, the momentum of this might be minus 2, and then therefore they cancel out. The reason it's minus is because it's going the opposite direction of the first one. And so that's a good way to keep in mind these sort of things. And this is how you, is to make sure you got your directions, you're taking care of that. Which way are these objects going? Now we've actually shown, and I've actually gone through all of the basic types of collisions with you guys. We've talked about what happens when you have a collision with an object and it hits the other object, and then the next thing that happens is that both of them are still moving forward at different speeds. We talked about what happens when an object collides with another object and it bounces backwards. You could even hit something with such a force, like the perfect amount of velocity, that it stops moving, but the other objects might start moving. That's actually possible. It happens a lot when you play snooker or pool. It's like you hit the white ball into another color ball, and then the next thing you know, it stops moving, but the other ball flies off at the same speed, and that's a transfer of momentum. The only one that we've discussed as well, what happens if 2 objects get stuck. And then so they get stuck and they start moving as one. But the one that we haven't talked about a couple of them. We haven't talked about this idea here of objects flying apart. But the other one that we haven't talked about is we haven't talked about, well, what happens if they're traveling in the opposite direction? You know what? This is actually a good idea for an attendance question. I'm going to actually might do that, like, you know, tomorrow's attendance question. To like a 300 gram, you know, a 300 gram egg shape, plastic egg shape is attached to a 200 gram with a spring in the middle, and they both fly apart. And, you know, yeah, I think you guys can work that out. Anyway, I will get to that. But the one we haven't done is one like this. So what I want to do is like a sticking collision, but this time it's a sticking collision where both objects are going in opposite directions. And this is another really good example of where it's important to keep in mind direction. If you don't keep direction in mind, you could have a bit of an issue. It's a bit of a depressing scenario here, ladies and gents, but I'm like, you know, it's kind of was like the best scenario I could think of, but we're going to go with it anyway. The driver of a 12-ton truck, 12,000 kilograms, is moving at 12 meters per second, falls asleep at the wheel and crashes into a 1,500 kilogram car traveling towards it at 16 meters per second. So there needs to be a comma or a full stop happening in this sentence. That's a really bad sentence, but yeah. The two vehicles merge together. What is the velocity of the car after the crash? I've also forgotten the question mark. So, and by the way, ladies and gents, I said this is depressing, but this does happen a lot. The truck drivers get paid, you know, for moving something from one place to another. So they will sometimes do back-to-back shifts, and sometimes they can get very, very tired. Luckily for us in Australia, we have legislation to protect drivers, so they can't do, I think they can't do more than 12 hours of work or something like that without having a 6-hour break or something like that. But in America, there's not really that much protections, and so therefore some bad accidents happen. So let's draw our truck. Here is our truck. It is 12,000 kilograms. It's moving at 12 meters per second. Then there is a car crashing to 1,500 kilograms traveling towards it. So there's a car that's actually here that's traveling towards it at 16 meters per second, but it's only 1,500. And then afterwards, together they are both moving together. But here's the interesting thing, right? We actually don't know which way these things are moving. And the only way to calculate which way these things are moving is, and by the way, the net mass here. Can someone tell me in chat, what is the net mass of these two objects? I want to know what the net mass is here. So someone calculate that for me. But we actually don't know which way these objects are moving. They could be moving to the left, or they could be moving to the right. So I'm actually not going to draw an arrow. They might even be arranged in such a way that their momentums cancel and they don't move at all. So let's figure this out. Who's got that net mass for me? The net mass is, come on guys, in chat, tell me what the net mass is. 13,500 kilos. Thank you. Just by adding those two numbers together, 13,500 kilos. Now, let's do this. So the momentum initial must equal our momentum final. The initial and the final momentum must be the same. Our final momentum is going to be mass times velocity, which is going to be 13,500 times whatever the velocity is. Whereas our initial is going to be the mass of the purple object, mass of the truck, times the velocity of the truck, plus, in this case, the mass of the car times the velocity of the car. Now let's do this. So the mass of the truck is, I'm going to go back to black now because I'm going 12,000 kilograms, and that's moving at times 12 meters per second. Whereas the car, that's traveling at 1,500 kilograms, but it's traveling at, in this case, 16, but in the opposite direction. So we're going to write times negative 16. Just so that we remember that this 16 is in the opposite direction. That's why there's a negative here. Let's do some quick maths. 12,000 times 12 is going to be 144,000 in this case kilogram meters per second, minus 15 times 1,500 gives us 22,500 kilogram meters per second. That equals 13,500 something. So if we just solve this out now, all we need to do is we need to go 1,400 minus this. Oopsies, I haven't got enough zeros here. Yeah, no, that's right. But then the other one is 1,500 times 16. Ooh, what did I do wrong here? 24,000. I don't know what I did wrong there. Sorry, guys. That looks a bit better. So now if I figure out 144,000 minus 120,000 divided by 113,500, that should give me that final velocity. That final velocity is 8 point, I'm going to round this to 2 decimal places, to 1 decimal place, 8.9 meters per second. And then we have to give a direction. So I'm going to give a direction in this. I'm going to give the direction as the same direction as truck velocity. There we go, and you can do that. As I said, your direction can be anything. In this case, though, I want the direction just to indicate, yeah, it's going to keep moving in the same direction. Does it ask for velocity? Yeah, I think it does. So that means that after the crash, this is going to be moving this way. And like, you probably could have guessed that. We've got this massive, super heavy truck. And then we've got this tiny car. The truck is going to massively outpush the car, is going to be what I'm trying to suggest here with this equation. And ladies and gents, that's the end of the lesson. Not only am I annoyed because I was going to give you guys a chance to work on some questions, but I'm also sitting here thinking, oh my God, like I've spent the whole time talking about this. What I'm going to get you guys to work on next time, and actually we might actually do this, but give you guys the whole lesson to work on 11.2. I haven't decided yet, but yeah, I'm going to give you guys 11.2 to work on for next lesson. I will give you guys some more information on that next time. I will let you guys go because this is now the end of period 3. Thank you so much for listening. And if you guys need some help, if you guys don't know how to do these types of questions, please send me an email. I can organize a private video, a private Zoom, whatever you guys need. But otherwise, yeah, good job. Keep it up, and I'll see you guys next time.